roll them in. These are some of my favorite math stories. In this episode, mathematics is the prisoner's dilemma. We'll explore a particular aspect of game theory called the prisoner's dilemma, along with some extensions of it. We'll see some insights into animal behavior, including human altruism and guppy protection. Game theory was first developed in the 1940s by the great John von Neumann and others. A better name for game theory might be competition theory, because many of the games considered are militaristic or industrial. The prisoner's dilemma game is famous due to the truly paradoxical nature of its solution. I always found the names involved with the prisoner's dilemma a little confusing, but let's start there anyway. Two people have been arrested for a crime and are interviewed without any chance of communication. They are each offered a deal. If you confess and your partner does not, you will go free and your partner gets a 10-year sentence, and vice versa. If you both confess, you both get 8 years. If neither confesses, you each get 4 years. What would you do? To try to get confessions, the interviewer provides some helpful analysis. You don't know what your partner's going to do, but if they confess, you need to confess also to avoid the 10-year sentence. If they don't confess, you should confess and you will go free. Either way, you should confess. The best outcome for the two of you would be for neither to confess, but the better choice for each person individually is to confess. A real paradox. Selfish interests conflict with overall interests. Here's why I think that the language is awkward. For animal behavior, we want to frame this as whether the two animals cooperate with each other, equivalent to not confessing, or defect, equivalent to confessing. Should you save your partner from the bus, or throw them under the bus? In this context, each individual has a selfish incentive to defect, but the better overall solution is for each to cooperate. So how do you explain altruism, where one person sacrifices for the benefit of others? The repeated prisoner's dilemma can help us. To follow this, let's use the following point system, modified from our criminal story to make higher point totals better. If both cooperate, both get 6 points. If both defect, both get 2 points. If one cooperates and one defects, the cooperator gets 0 points, the defector gets 10 points. What happens if you play the game repeatedly against several other players in a tournament? This is the repeated prisoner's dilemma. As we've seen, you're better off defecting against one player in one round. But if you defect against me one round, I'm unlikely to cooperate with you next time, and we could have several rounds getting just 2 points each. Meanwhile, two players who get into a pattern of cooperating are racking up 6 points per round. In the 1980s, Robert Axelrod organized tournaments to try to find good strategies. Each player submitted a computer algorithm describing its strategy. The shortest program, submitted by Anatole Rapoport, was a tit-for-tat program. The first time we play, I cooperate. Then I mimic you. If you cooperated last time, I cooperate next time. If you defect, I'll defect next time, but then reset to cooperation. And this program won. In some ways, then, tit-for-tat is a great strategy, encouraging cooperation but punishing defection. Does this ring true with you? In your social interactions, do you tend to be nice to those who are nice to you and retaliate once against those who are mean to you? It seems that this strategy has found its way into guppy behavior. In an experiment, two guppies were in a tank with a sleeping predator. Actually, a mirror image, the guppies were safe. Food was sprinkled near the predator, tempting the guppies to swim close to the predator to feed. Sometimes the two guppies would swim over together to eat, giving the predator a confusing prey. Other times, one of the guppies would swim part of the way over and then defect, leaving its partner unprotected. The guppies remembered which ones defected and would not cooperate with them on the next feeding. A different experiment with the repeated prisoner's dilemma may give some insight into the behavior of all animals, including humans. Imagine a large grid of pixels, with each pixel representing a person. Each person plays prisoner's dilemma against its neighbors, and everybody adds up their points. Each person A then looks at their neighborhood. Most have 8 neighbors, including diagonals, and then plus themselves. And find the person with the most points. Whatever strategy, cooperate or defect, the winner used, person A uses that next time. That sounds reasonable. Look around for who's winning and copy them. What happens in the long run? The images here show the result of an experiment in which we start with all cooperators except for one defector in the middle. That defector will win round one, taking advantage of all of its naive neighbors. The first image shows the defector in black in the middle with a blue ring of neighbors who will copy it and defect in round two. Subsequent images show the progress of this society, with purple being a person who defected last time but will cooperate next time. By the fourth image, it's looking like defection will take over, but then it breaks up in image 6, and as the game continues, there is a beautiful kaleidoscope of behaviors displayed. Eventually, the percentage of defectors reaches an equilibrium. It'd be different percentages for different choices of points, but individual people remain fluid in their behavior, defecting when a wave of defection comes through. Isn't that amazing? Now, nobody is saying that this is a realistic model of animal behavior, but it is instructive that starting with some simple rules that have each person playing selfishly produces a dynamic society in which good and bad behavior oscillate almost unpredictably. As the hyperlogical Mr. Spock would say on Star Trek, fascinating.